Yo, what's up? Welcome back to the Sexy Challenge YouTube. So, today we're going to talk about constant acceleration. As we know in physics, we know what is acceleration, right? Acceleration is a delta of b or delta, basically change in velocity over time, basically. And we know acceleration, but what happens when we have constant acceleration? Well, when we have constant acceleration, the velocity in this case is linear, right? It increases linear. So, no, cut that shit. I don't even know. Well, when you have constant acceleration, there's a very interesting thing, because since we have a constant acceleration is constantly increasing, then there's a very interesting, unique scenario where we can basically calculate, like basically solve any problem with shortcuts. Because since we have a special scenario, then we can take advantage of that scenario and basically have shortcuts. Take advantage of that scenario to solve the problems. Obviously, only when we have constant acceleration. So, what are those shortcuts? Basically, it's four equations that we can basically come up with, and have these shortcuts, these tools to still solve any problem involving acceleration. In this case, involving constant acceleration, but much faster. That's why it's a shortcut. So here we go. So we know obviously acceleration. I just put it out there. Now, there's some problems, for example, where we want to determine the velocity of an object, right? We want to know what is the velocity of an object. In this case, since it's a constant acceleration, we want to know what's the velocity of an object, knowing the constant acceleration, right? So in this case, we're gonna basically use the equation that we had previously, which was delta velocity, which basically meant final velocity minus initial velocity over time, and basically solve for the velocity. In this case, final velocity, because there's two velocities, the initial one and the final one. We want to know final velocity. So we solve for that, and that gives us. I'm just gonna solve it, bro, because I think it's just so much easier if I solve it. It's not that fast, but we can follow along. So we need to solve for b, for final velocity. So we multiply times 7. We have a 3 8 minus b0. We solve this. So now we have there you go. So that's the thing we have. Hopefully you can see it. Yeah, you can see it. So that's basically very helpful, because now we can just solve for that knowing the constant acceleration, right? Now let's say we want to know also the position there, because sometimes we also want to know the position. Well, we know that. So we know the position of an object, and we can basically get from that get the position of an object from the average velocity equation, right? So the average velocity equation, I haven't wrote it down. It's basically delta x over time, delta x. This is basically the change in position. So final position minus initial position, and in this case we can solve for final position, because that's what we want, right? So solving by that, I'm gonna solve it right here, all out right here. So times t also, and we get to sum it up. And then we basically get this. Okay, so we basically get this, right? this is not the final question we want to get to. It's just a way which you can get to the position, right? Now, what if we want to know what is the average velocity? Knowing that we are in this constant acceleration game, right? This constant acceleration situation. So, in this constant acceleration situation, basically, from the initial velocity to the final velocity, it's gonna be a linear growth because it's a constant acceleration, right? And basically, if we want to know the average, right? What's the average acceleration of this? Well, it's basically half. So we chop through it, boom, it's basically half. So what does this mean? This basically means that the average acceleration whenever we have the average velocity whenever we have constant acceleration, it's gonna be the initial velocity plus the final velocity divided by 2. Now, this only applies when we have constant acceleration because of the nature of constant acceleration, right? Now, knowing that, let's actually go to the situation where we want to know the final position, right? In terms of constant acceleration. So, in that case, we already wrote that in here, which was basically the final position being equal to the initial position plus the average velocity times all the time. And in this case, what we can do is plug this, as you can see, is the average velocity into here. So it basically gets us this times that. And we can also plug the previous equation that we talked about into here, into the final, into the final velocity, okay? So that one is the equation that we previously had, which was, in case you don't remember, this one of final velocity being equal to the initial velocity plus acceleration, in this case constant acceleration times time. So we can plug this in here. So that would be plus this plus 19 divided by 2 times time. Okay, so we got that. Now we can simplify that into a much more easier way to understand. So that will be the following. Oh, hopefully you're seeing that. Yeah, you're seeing that. So that will be the following. We have this, and then we will have the initial velocity times time, and then plus half of acceleration times time. So this is a more easier way to understand, and this is another one of those very useful equations. So at the very end, I'm just gonna write the 4 equations because it's basically 4 tools, 4 shortcuts, 4 equations that are very useful tools that helps us know and solve problems whenever we have this scenario of constant acceleration, right? So we have this one, which is gonna be really helpful. And as you looking at it this way, okay, yeah, this is gonna tell us the final position. But the interesting thing here is that you can essentially convert, like basically play with this equation, where you can solve for any of the following variables using this equation. So that's why it's a very useful tool. That's why all of these are very useful tools, because you can essentially not only, you can essentially take these tools and use them as they are right now, which in this case will be final position, but you can also rearrange it into certain ways to solve for whatever problem you're solving. Now, all of these, remember, is under the condition of constant acceleration. So all of these works, just all of these shortcuts work because we were talking about constant acceleration. Yeah, that's the beauty of this. This is a really useful tool. Now, what if we have no time? What if we don't know the time? Like, what if we try solving a problem, we don't know the time? So in that case, we have what is called the timeless equation. So this timeless equation, we basically are going to substitute the equation that we had here previously, which was the equation of the average velocity, into the equation of the, so that's basically going to be, okay, so we have this one, which was the one of the final position, as we previously noted. That was the one of the final position that we solved for x. And as you know, here we're gonna basically replace the previous one. That's gonna be boom, 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 and that's gonna be this. Okay. Now, next, what we need to do is that we need to solve for time in the equation that we had of the final velocity. Okay, so the equation that we had of the final velocity was final velocity, which equaled the initial velocity plus constant acceleration times time. So in here we're gonna solve for time, a boom boom, and we basically have this. There you go. And now we substitute that into the previous equation that we have, this one, which in this case you can see is the time. So we're gonna substitute that into here, and that's gonna be the following. Boom. Right? Now we can obviously make this be much clearer, much more simpler. I'm gonna actually do that right now. So now we got that one. Normally people just solve for the final velocity squared. Basically solve for this, which that's how a lot of textbooks present it, so that's why I'm doing it this way. But yeah, let's do solve for this, which gives the plus the 2 minus x. There you go. So this is the last one, the timeless equation, that is really helpful whenever you know the time. And yeah, I'm just gonna go straight to providing the full four equations. That, as I said, like the basic thing. I mean, the equations that are there, right? So it's not like you gotta memorize them. The thing that we gotta understand here is that these equations that I'm gonna present are basically the shortcuts for when we are dealing with constant acceleration. So when we have a situation where we are dealing with constant acceleration, these are going to be really helpful tools and really helpful shortcuts into solving whatever problem you want to solve. Okay, so that's basically the one of the velocity, the final velocity, which is the initial velocity plus constant acceleration, and then time. The other one of the final position, which is the initial position plus the initial velocity, times time, and then plus 1/2 of constant acceleration times time squared. And then the other one is this one, and the other one that I said also is this one. This is average velocity, which was initial velocity plus final velocity divided by sorry, I mean it's the same thing. I'm just gonna put it this way. There you go. Final velocity plus initial velocity. Alright, so these are the 4 tools that I. Can you see that? Shit, you cannot see that. Well, basically the sun is in here, but these basically I'm saying. Let me see if I cannot move that shit. Whatever. Here are the equations. As I said, the important thing to understand here is that whenever we have a situation where we have constant acceleration, where the acceleration is constant, we can basically have these tools that make us get into a shortcut, right? It's great shortcuts in order to solve whatever problem we want to solve. So let me actually give an example. So I'm just literally going to read the problem that I have right now. So in designing an airport for small planes, one kind of airplane that might use this airfield must reach a speed before takeoff at least 27.8 meters per second, okay? And accelerate at 2 meters per second squared. In this case, as we said, it's a situation of constant acceleration. So in this case, the acceleration, which is 2 meters per second squared, is constant. So we basically want to know if the runway is 150 meters long. We want to know if this airplane is going to reach the required speed for takeoff. And if not, what is the minimum length the runway must have in order to take off. So I'm going to solve the problem knowing this. So from this, to solve the problem, from the 4 equations that we have, the 4 tools, right, that we have, this one right here is going to give us what we want. So in this case, we need to solve for v, for velocity, in this one, okay? So let's do it. I'm going to put the data that we have, so we know that the constant acceleration is 2 meters per second squared. What else? Oh, then the distance is 150 meters the wrong way. And that's it. And here's the thing. We can know the velocity without the time. That's why we're using the timeless equation. And as you can probably tell, on the problem that I described, they never mention time. So that's the that's the power of this. This is an example. So this one we can basically say it's 0, right? The initial velocity is 0 basically. So we basically have this times this, okay? So we need to solve for this, so let's do it. So we have 0, so we have 2 times the constant acceleration, which in this case is 2 meters per second squared, and then that's times this. This is basically delta, the change in position. That's basically this, right? The distance. Okay? So that's there you go. Okay? That basically gives us 2 meters squared per second squared. Now finally we need to get rid of the square, so boom, 24.5 meters per second. So now here's the result. This is the velocity required for the airplane to take off. Okay? Now, as we know, the runway length is not sufficient because the minimum speed is not reached. Okay? As we said, the object must reach a minimum speed of 27.8 meters per second to take off. Here, it's much less than that. So, can be done. Now, knowing that, we gotta go to the second question, which is, if not, which is the case, what minimum length must the runway have? Now, for that, we can basically use this equation again. what a surprise. That's what I'm telling you, man. These are great these are great tools, okay? So, and why? Because well, we have this, we are basically gonna solve for this, which is the gonna we are gonna basically know what's the necessary distance for the airplane to take off. Like what's the necessary distance that the airfield needs for the airplane to take off, knowing that it's going at this velocity. Okay. Basically solving. I'm just gonna do it very quickly. So solving for that is gonna give us the following, which is it's gonna give us this. Maybe that's divided by 2a. Okay. Yeah. So that's where we at. So now we just gotta do it, right? So now we know. I'm just gonna put it this way. I mean, this and this is basically the same thing. So, what is the final velocity we solved for? As we said, was 27.8 meters per second. So in this case, 27.8 meters per second squared minus, okay, this is not gonna be enough. Let me get rid of these ones to have space. Okay. And as we know, as I said, this is basically 0, so I don't even need to write it down. And times, and divided by, or over 2 times the constant acceleration, which as we know it was 2 meters per second squared. 2 meters per second squared. There you go. So that's what we have. So now we just need to solve it, and that I'm not gonna solve it right now. It basically gives us the following, which is 193 meters. So by solving this, it basically gives us 193 meters, and that is the necessary length that the runway from the airport must have in order for this object in motion, which goes at this velocity, at this final velocity, must take off. Because yeah, as you can see, 193 meters versus the 150 meters we have is way different. So I don't know, man. Hopefully this was not confusing. Basically, this is a great example of how, in this case, the timeless equations without knowing the time can get us to know, well, what do we solve for? And yeah, basically, the thing to get from this is, okay, whenever we are at a scenario of constant acceleration, the nature of constant acceleration allows us to have shortcuts, which are these 4 equations that I previously had. And those 4 equations I previously had are really great tools and shortcuts that can help us to solve any problem we want. That's basically it. Okay, that's basically it. Like, I mean, don't memorize the equations. Like, it's just, the thing here is, hey, we need to understand what is this about. And a lot of people just want to memorize the equation without even knowing what is the why of all of these, and but that's basically the why. Okay, so they're great tools, help us whenever we are at this scenario of constant acceleration, and that's it. Like the equations pretty much are great tools. You need to memorize them. If you want, whatever, you can do that. Yeah, basically that's the nature of constant acceleration and how you can take advantage of it to solve your stuff. There you go.